The atomic theory was originally proposed by the Greek philosopher Democritus in the 5th century BC. He speculated that everything in the world is ultimately composed of combinations of small, hard, and indivisible particles. He called these particles atoms, which in Greek translates to indivisible, and suggested that they came in various shapes and sizes but were all made of the same basic material. The modern scientific theory of matter states that the great variety of substances we see in the universe are made from combinations of different chemical elements, and these elements do indeed consist of trillions of atoms, which themselves are made up of even smaller particles. Now, to be clear, today the atomic theory is much more than a theory. It's an undeniable fact. Not only can we see individual atoms using electron microscopes, we can even trap them and move them around using frickin' sharks with laser beams attached to their foreheads.
Are those sharks with laser beams attached to their heads?
Okay, not the shark thing, but seriously, we can move them around using lasers. Frickin' lasers. So when we talk about atomic theory, we don't mean the theory that states that everything is made of atoms, but rather the theory that describes how atoms behave and interact. The internal structure of an atom is specific to each element and gives that element its particular properties and characteristics. For example, a hydrogen atom is constructed differently than that of an atom of gold. Modern atomic theory kicked off in the early 1800s with the work of English chemist John Dalton. The idea that matter is composed of tiny indivisible particles was not generally accepted until after his 1808 publication of A New System of Chemical Philosophy. In his paper, he proposed that each chemical element is composed of atoms of a single, unique type, and though they can't be altered or destroyed by chemical means, they can combine to form more complex structures, aka chemical compounds. And this marked the first truly scientific theory of the atom. But it wasn't until 1905 that Albert Einstein came along and proved the existence of atoms mathematically in his famous paper on Brownian motion. Up until that point, scientists were unaware of the existence of an atom's nucleus and thought of an atom as a web of positively charged material with negatively charged electrons peppered throughout, like cherries in a cake. This model of the atom was just used as a metaphor to describe what was thought of at the time as a uniformly dense distribution of stuff within the atom. However, a few years later, this model was destroyed by Ernest Rutherford, who was the first person to actually look inside an atom. He was able to do this using an experiment where he bombarded a thin sheet of gold foil with alpha particles. Side note, an alpha particle is just the nucleus of a helium atom. Most of the alpha particles went right on through the foil without any kind of significant deflection, but a few bounced straight back. Rutherford and his colleagues originally thought they would observe the alpha particles slowing down as they passed through the foil, kind of like a bullet being fired through water. But instead what they saw was evidence that most of the mass of the nucleus was concentrated in a very small part of the atom. On top of that, the nucleus must be positively charged, since particles with a negative or neutral charge wouldn't deflect the positively charged alpha particles. This observation is what led Rutherford to propose the atomic planetary model, in which a cloud of negatively charged electrons surrounded a small compact nucleus with a positive charge, which is why in most science classrooms you'll see a picture of an atom that looks like this. However, this kind of diagram is misleading because the size of the electrons, protons, and neutrons, as well as the distance between them, are severely disproportional. Okay, this is the part. In reality, the nucleus has about 100,000th the diameter of the whole atom. To put this into perspective, imagine that a hydrogen atom is as large as a professional football stadium. Now imagine the Pope with a different funny looking hat. Oh, Pope, you so crazy. Okay, now back to the atom football stadium thing. The size of its nucleus would be about as big as a grain of sand that's sitting on the middle of the 50-yard line. So as you can see, the vast majority of an atom is made up of empty space. And since all matter, including you, are made of atoms, you are mostly nothing. I know, right? Underneath an apple tree, when an apple suddenly fell from the branches, hit him on the head and knocked him unconscious. When he finally woke up, he had a vision that would revolutionise. Okay, now in reality, empty space is mostly not empty. And this is because electrons and photons don't interact with quarks and the gluon field fluctuations and other stuff that goes way over my head. But if you're interested in learning more about this, Derek from the channel Veritasium recently made an excellent video which explains this. So if you want to watch that video, you can click right.
Well, this may not be as strange as it first appears.
Field fluctuations, where the